Oh, no, okay. Okay, good evening or good morning or good afternoon, anyone, wherever you're joining us from. Women in Machine Learning and Data Science is a voluntary organization that's intended to support women and other minorities in the field. And this is the Brussels chapter, a relatively new chapter. We founded it just before the first shutdown. So we didn't even manage to meet in person yet. This is only our third talk, and we have very exciting speakers today. I'm particularly happy to announce the talk about climate change, AI. That is how I found about Jessica Penn. She's a product manager at QuantumBlack, but at the same time, a core team member at Climate Change AI. They are just like us. They are a volunteer organization of people who work in academia and industry and who are interested in research on topics that involve fighting climate change using machine learning and data science. And this is exactly what really the European policy is all about right now. We are right here in Brussels based, and we follow the EU policy making closely. And the main conclusion is that the recovery and the growth after the COVID has to be both green and digital. These are the most important issue. And I guess Jessica will tell us more about climate change and artificial intelligence and the work that is being done both by her and other people at the organization. And the second talk I'm personally very, very excited about, because I'm economist by training, and all of my life I've been basically working on methods that should allow for causal inference. Only recently, basically, I entered into the machine learning field, and then I discovered this focus of people in machine learning field on prediction, which is a little bit more different than causal inference. So there was this, basically, from my perspective, clash between how to unite these two fields or two interests in social sciences being on causal inference, and then in machine learning field being on prediction. And I'm particularly interested in how we can use machine learning methods for causal inference, and that will be our second talk. So without any further delay, I will now let Jessica introduce herself, share her screen, start her presentation.
Great, thank you very much, and it's a pleasure to be here with you all today. Apologies in advance that my camera is not working, so I won't be able to turn my video on. So thank you so much for Women in Machine Learning and Data Science for inviting me to this talk. I am a product manager from QuantumBlack McKinsey, and I'm also, as Maja said at the beginning, also volunteering with the Climate Change AI as a member leading their industry events. And I have the pleasure of speaking to you a little bit about our work in the space, showcasing some of the use cases that we can address with AI and ML in tackling climate change. And yeah, so if you have any questions along the way, just feel free to post them in the chat, and I'm happy to take them at the end. So let me share my screen. Just going to go into presentation mode. Can you guys see the full screen, not the presenter mode?
We can see the presenter mode only. We can basically just see the half of the screen.
Yeah, it's I don't know, I don't see it well.
Is that better?
No, it's still in the presenter mode. It's not the full screen.
Jessica,
now it's fine.
Okay, great.
No,
sorry.
Yes, it's fine.
Now it is still in presenter mode.
It's still in presenter mode?
Okay.
Yeah, so if you click swap displays, it should probably help.
Yes, perfect.
Okay,
yes.
Okay. Sorry. It's an endless Zoom problems today. Okay, so just going to introduce what we do as an organization, showcase one specific use case, and talk about some of the other use cases that we do. So for those of you who may have heard about Climate Change AI, we are a global organization of volunteers from academia, industry, and policy who work at the intersection of climate change and AI. We try to cultivate a global network of entrepreneurs and investors and provide digital resources for those looking to work in this space, as well as provide advice to stakeholders from individuals to public sector on how they should best leverage AI to tackle their challenges. So CCI is present at all of the leading AI and ML conferences, including ICML and Europe's, as well as the climate change conferences such as COP. So I won't spend too much time on climate change. I'm sure we all know enough about it and have heard, you know, it's something that pops up on our newsfeed all the time. But, you know, as an organization, we are really just trying to leverage our skill sets to try to address this very important and imminent problem that's going to affect all of us in the coming decades. So one of the key assets that we created was publishing a paper called Tackling Climate Change with Machine Learning, where we try to create a really comprehensive overview to identify where can we leverage AI and what kind of problems can we actually tackle. So this is a paper that aggregates and informs all of these use cases across a wide range of subjects and topics and areas, and also provide recommendations on how we move forward. So really useful starting point for anyone wanting to learn more. Within that paper, we look at you know, the sort of mitigation and adaptation subject areas. So that can be things like electrical systems, transportation, all of the things listed on the left. And then we map those against techniques such as forecasting, remote sensing, optimization, you know, typical AI ML techniques against those use cases. So in the paper, this is just a cross-section to show some of the use cases mapping against the subjects and the techniques. And I'll be diving into using remote sensing to understand some of our social systems and structure in the next couple of slides. So just as a to give you a sense of the type of use case we can do, so QuantumBlack partnered with the Smith School of Economics and Enterprise and the Oxford Martin School to help them expedite their post-carbon transition program. And one of the key things that they are trying to do is to identify something called SIPs, which are sensitive intervention points. There are essentially these network nodes on a graph where we say, rather than trying to tackle everything all at once, how can we identify these intervention points such that a modest action can actually trigger an outsized response, and therefore using the network effect to amplify the intervention that we are trying to do. So our problem statement was, how can we identify these SIPs within a global fossil fuel supply network so we can better target intervention of decarbonization and you know, and where to focus on for the energy transition. So we try to create an asset level data network to map out this fossil fuel supply network to, as I said, identify these SIPs And the people that we were trying to solve for are, people like researchers and private enterprise and government organizations. And the challenge is that, as you can imagine, the global fossil fuel supply network is huge. It's very complex, and really is a perfect use case for leveraging machine learning to try to understand the interactions within it. So we analyzed millions of assets and tens of millions of connections in order to create something that looks like this, which is a map of the global fossil fuel supply network with different assets such as coal mines and power stations and shipping ports and rail routes. And the idea, as I mentioned before, is with this queryable graph, where are these intervention points where we can really have a much greater impact on the overall network. So we so the approach that we took was to leverage 12 different types of data sources that covered all of these asset types, and then leverage techniques such as GeoPandas and Neo4j in order to create this queryable network. And what we came up with was a network that had 11 million nodes and 20 million relationships, where you can write queries against it to understand the sort of paths between them, and therefore infer the weights and understand the relationships between these fossil fuel assets. So this culminated in a paper that we published earlier this year, and this is now available online for further research. So this asset is open sourced and can help answer questions such as, again, to reiterate, what is the most effective way and efficient way to decarbonize? How can we identify these extremities, or do we start from the center? This is just the beginning, and sets a foundation for further research and further development. So just gonna skip over and talk about some of the other use cases. So the previous one is using remote sensing techniques. The other ones are listed here. So this one is somewhat similar, but we are also using satellite imagery and large corpuses of text to gather decision relevant insights, such as tracking greenhouse gas emissions real time and pinpointing deforestation. And one use case is that we can use satellite imagery to identify areas that are susceptible to drought, and understand where we're seeing excessive rainfall, and monitor crop yields in order to inform better farming practices and emergency response. So this has been, widely used by government programs such as the NASA Harvest and other NGOs across the globe. The next group of use cases just want to highlight is forecasting. As I'm sure we are all aware that this is one of the understanding and forecasting energy demand is critical to help us expedite and deliver the energy transition. And being able to predict renewable energy supply in order to better optimize power systems is one of the use cases that we often see. So in the area of forecasting or nowcasting, we can use AI and ML to understand and predict cloud coverage in order to understand how much power you can generate from solar PV at any point in time. And this is then fed into let's say the national grid in the UK to help them forecast and balance the grid. Another key area that we see with AI is on improving the operational efficiency of existing systems, such as reducing waste and help help systems operate more effectively. So we see this in transportation systems, reducing the optimizing the supply chain of food and fresh produce, and also optimizing heat and cooling systems in buildings. So one typical use case is using this on a HVAC system, so that's heating, ventilation, and cooling system, in order to better identify usage patterns and equipment constraints. So we can leverage things like reinforcement learning to better control these HVAC systems in residential, commercial, and industrial buildings. The next theme I want to highlight is around predictive maintenance. So understanding, this is really, how do we understand failures and try to anticipate them before they occur, since fixing them can both reduce leakages such as methane from oil wells, and make infrastructure more resilient. So one use case of this is to help with the maintenance of rail systems. As we all know, rail systems are critical to decarbonize the transportation systems, and predictive maintenance can help increase the competitiveness of these systems by helping them run more efficient and on time. And entities such as the Deutsche Bahn in Germany have already begun to use AI to analyze large amounts of sensor data at scale in order to detect anomalies that could be occurring in the future. The next set of use case is on how AI can help us accelerate the process of scientific experimentation itself. So in the development of new materials for batteries, or for other types of technologies, and maybe even carbon capture and green steel and green cement. And the way that we apply AI and ML here is that whilst it can't really necessarily replace the process of scientific experimentation, it can be used to analyze patterns in past experiments in order to better understand which next experiments are more likely to be successful, and try to, in that process, intelligently recommend which materials it might be good to try next. These use cases, again, are a bit more experimental than the previous ones, and its sort of maturity is slightly lower than the ones I described before. And the last theme I want to highlight is leveraging AI to approximate time-intensive physical simulations, such as climate models, energy models, and models associated with city planning. So in these cases, there is often a very time-sensitive model that would take a lot of computational energy to execute. And we leverage AI here to help speed up or slim down some of these models. So looking at this climate model in particular, where there's a need to downscale them or to make their predictions more localized, we can use AI to do that. One thing to highlight is that, we can use AI to enable these localized simulations by running fast approximations to time-sensitive parts of these model, and again, make them more efficient. So these are the 6 types of areas that we typically see that the most mature application of AI and ML. And again, you can find more details about them in the CCAI paper, as well as the publication of the fossil fuel supply network that I talked about before. But I do want to caveat to all of this when we consider AI. So as we all know, AI ML is a highly loaded term, and people use it sort of often without rigor and think that it's a silver bullet. So from our work in CCI, we typically see that climate change mitigation and adaptation often don't benefit from AI at all. For example, smart buildings might bring improvements, but building installation might be an easier and more impactful first step. So even when AI is applicable, we always say that is part of the strategy, is a tool that can accelerate and enable other work, but it's never a silver bullet. It's also neither intrinsically good nor bad, and it can be used to make it can be used in applications that can make climate change worse as well. For example, AI is being used extensively to accelerate the oil and gas exploration and extraction process, which has actually slowed down the transition to low carbon energy sources. So I've just talked about these things, which are which only really have its impact if they get deployed at scale in the real world. And that's why I just want to spend a couple more minutes to talk about some of the barriers to deployment and what can be done to alleviate them. So whilst some AI models are powerful and complex, it's generally good to start with a simple method as possible to begin with. For example, regression, as we know it, often works much better than anything overly complex. Second, many AI applications improve efficiency, but as we see with all efficiency applications, we also have to mitigate the rebound effects. For example, self-driving cars increase emissions overall if they make driving easier and cheaper, which result in more miles being driven. And the climate impact of self-driving cars will depend on exactly how that technology is being developed and the policies that surround it. Next, it's important to remember that new technologies can exacerbate inequalities in society unless taken care of, and we should be mindful that those who have access to control understand its implications, and the technology is shared as equitably as possible. And the last thing is that partnerships are key to alleviating all of these potential downfalls. And that include researchers in AI and climate relevant fields, industry and other entities implementing the work, the end users and the communities that are impacted, and policymakers regulating the space. So lastly, if you are interested in finding out more about climate change AI, I encourage you to go onto the website where you can find a corpus of information and resources, including the paper that I outlined. We also have happy hour that happen on a fortnightly basis where you can discuss these topics with like-minded individuals. We also and the best way to learn about all of these up and coming events is really just to sign up to the newsletter. So we send those out monthly, and that has information on all of the latest research, job postings, network events, and other events such as webinars and summer schools that we host. And with that, I will conclude. Thank you for listening, and happy to take any questions if anyone has any.
Okay, I will. Whoever has a question for Jessica, many thanks, Jessica. Please, you can unmute yourself. We are in a very small company, and you can ask the questions directly to her. You can unmute, all of you. I allowed you to unmute. In the meantime, Jessica, I have a question. I would be very interested in seeing this code behind the fossil fuel supply chain, do you plan that at any time you post on GitHub something that includes the code and something like sample data so that people can see your usage of GeoPanda and the graphs?
Yeah. The code should be on GitHub already. It should be linked from the paper. So all of the things that we used were open sourced, including all of the libraries and the data sets. So everything is open source essentially, and it should be, well, hopefully relatively reproducible.
Oh, so it's already on the GitHub. Yeah, okay, that's great. Yeah. Okay.
Hello, Jessica.
Hi, Farah.
Firstly, I would like to say thank you so much for, hello?
Yeah, we hear you.
Okay, so firstly, I would like to thank you, Jessica, for this event. I really enjoyed, and you gave me really a lot of information. And also, I would like to ask about something. What do you where do you see the world after 5 years in the zero carbon path?
You mean in terms of the sort of overall energy landscape, or in terms of AI and ML?
No, in terms of energy.
In terms of energy, I mean, we only really have the next 2 decades to set ourselves on a path to avoiding climate catastrophe, in my mind. And I think if we follow the IEA projection about how the world should decarbonize, we should see in the next 5 years that our share of renewable energy use is at least twice as much as what it is today. I would say I'm somewhat pessimistic about that given the current trajectory. However, there is at least a bit of room for optimism in the sense that policies such as the sort of Green Fund from Europe and the Green New Deal from the US shows that there is a concerted effort by politicians to try to tackle this. I'm not sure whether we'll see that materialize and translate into reduction of fossil fuel consumption in the next 5 years to the degree that we need. Like that, yeah, that's the part I'm not sure about. But I am relatively optimistic that we are moving in the right direction. It's just a case of, are we moving fast enough?
Yes, I think that what is the most important in these days, we must educate people about the climate change, and that will affect really everything. There are lots of cities that can disappear because of the climate change, like Alexandria, for example, in the future, Alexandria, Egypt. So yes, I'm really interested about this, about talking about the climate change.
Great, thank you, Farah.
Thank you, Jessica.
So Jessica, you have a question in the chat from Alessandro.
So could you describe the techniques that were used to characterize energy load patterns? Was the model used to suggest action or to predict demand? So the use cases that I highlighted was really to predict demand. I'm sure there are also models in place which are used to try to balance supply and demand and therefore suggest actions, but the ones that we typically see is really on how do we predict solar PV generation versus demand at certain times in the day, and try to understand how the grid is going to cope with that. I can share the presentation afterwards if you want, which has links to a couple of places where you can find out more about the demand-led use cases if you find out more. So sorry, if you want to find out more. So I'm not actually a data scientist, so I can't talk too deeply to what techniques was used where, but I can certainly share some resources if you're interested in digging a bit deeper.
Okay. Anyone else? I just wanted to wait a minute. Whether I find there is this also paper in the recently came out in Nation's open access journal, which is called it's part of the Nature group, you know, communications and environment, and the title is quite mouthful, but it says something like a country-based rate of emission reduction should increase by 80% beyond nationally determined contributions to meet the 2 degrees centigrade target. Yeah, so the emissions should increase by the reductions in the emissions should increase by 80% beyond the nationally determined contributions. And one of the things that the authors emphasize that they just deal with how much reduction is in emissions is needed, but they don't say how we get there. So what I get from your presentation is your paper is exactly should tell us or should be helpful in telling us how to get to decreasing those emissions by 80%.
I mean, I think, yeah, it's as you said, it's great to set targets, but you know, how do you actually achieve them? And I think in lots of cases we kind of set them with great ambition without really working backwards on, is that feasible? These use cases I described are certainly ways that us in the ML and AI community can contribute towards them in order to accelerate their impact. I'll be honest, from my work in QuantumBlack McKinsey, and also to my point towards the end of the presentation, often AI and ML is not the most effective approach right now. For example, the simple case of reducing emissions from buildings, which in the UK accounts for 35% of the national emissions. Just making sure that we insulate them is the cheapest and the fastest ways to do that, rather than necessarily installing IoT sensors and try to optimize usage here and there. I think at this point it's really all hands on deck. So we should explore all of these avenues, but we should definitely not lose sight of the fact that there are often cheaper and easier ways of addressing these challenges.
Yeah, I do hope we find a way there, because the paper that I just talked about actually estimates only 5% probability of reaching the zero emission target. So it's not very optimistic, not at all. So I hope we with all that we are doing and trying to do, we increase that probability somehow. Okay, thank you, Jessica. Unless someone else has any other questions or comments, now I will let Roxana.
Yes, let me share my screen. Oh, wrong desktop. Okay. Which one can you see?
We can see very well, yeah.
Okay, good. Yeah. Okay, so thanks for having me present today. It's actually 2 years to the day that I started at QuantumBlack, so it's a great opportunity to reflect a bit on some of the things I've learned since I joined the company, and in particular focusing on what I learned about causality and how we approach this topic at QuantumBlack on our client engagements. We actually last year launched an open source library called CausalNex to perform causal analysis using Bayesian networks. And I'll give a little bit of an insight into how that library works. But let me start by explaining my ongoing journey for learning about causality. And I definitely would not call myself an expert in this field. And I'm still learning about it. And it kind of started when I joined QB 2 years ago. It was right after my PhD, which was in network science. And then it turned out that some of my colleagues had an idea for a little R&D piece on Bayesian networks. And they saw I did a PhD in network science and thought, surely that's related. It actually wasn't that related. But it was a good way to learn about a new field, to just sort of take a very specific academic question. And in the end, I spent a few months on that with another colleague, and we published a paper, which I'll come to briefly at the end. You can also feel free to ask me at the end about the acronym for the algorithm, which is called Dino Tears, and has that emoji shortcut, which you can see on the slide. Okay, so that was step one, and it was an academic paper, so the topic was quite focused. But at QuantumBlack, when we actually need to be quite practical and solve end-to-end business problems for our clients, not just finding interesting patterns in data, but actually using that data to answer causal questions. And this is why some of my colleagues started building this CausalNex library. So after my work on the paper, I basically started using the library and also applying it on some of my client projects to really learn how to do end-to-end causal analysis. And then after a while, I took a step back and realized that my knowledge of causal inference is a bit patchy. So from an intuitive perspective, causality is quite easy. Humans are very good at causal inference, but actually making computers do it can be quite hard. So that's when I started reading some books. And you might have heard of the Book of Why by Judea Pearl. So Judea Pearl is one of the central figures in this field, and he kind of brought about this causal revolution, getting people in different fields to answer causal questions, not just from randomized control trials or A/B testing, but actually from more normal types of data as well. And his approach, he has like one specific way of performing causal analysis, leveraging Bayesian networks, but that's not the only way. So there's another group based at the Harvard School of Public Health, and they published this book very recently. It's called What If? And it's freely available online, and it kind of looks at a different angle for causal inference. I'm not done reading it yet, but I quite like the way it's written. So I would encourage you to check it out, especially since it's free. And my goal today is to basically convince you that causal questions are important if you're in a data-centric field, and just to give you some idea of how people think about these questions in practice. So maybe you're not convinced yet. Maybe you're quite happy with how you think about problems as a data scientist or data engineer, and you use random forests, maybe with some SHAP on top for interpretability. Why do we need causality? And actually, causality is not always needed. So let's say we're just trying to predict whether equipment in a factory might fail. In that case, having a high-performing predictive model is enough, even if under the hood, the model is just learning correlations. However, if we're in one of the other two columns, where maybe we try to understand why the equipment might fail, or even optimize the way the factory operates in order to reduce failures, then the conclusions we draw will be wrong without the causal angle. And just to give a silly example, if you look on the right-hand side here, we see that ice cream sales are negatively correlated with the average weight in a population. But that doesn't mean that encouraging people to eat ice cream is a sensible public health intervention for reducing obesity. And of course, here, this is an obvious case, but that's not always true with more complicated types, with more complicated data sets. And we really do need explanatory models to make causal sense before we act on their recommendations. So for the rest of the talk, I'll explain how to leverage Bayesian networks for causal analysis. And our goal is to start from some tabular data and get to the point where we can answer causal questions. And in CausalNex, we think of this workflow in 3 steps. In step 1, you learn the structure of the data. And basically what you get is a graph that tells you how different variables depend on each other, like we see in this example. And the output is called the directed and acyclic graph. Acyclic meaning that you don't just go around in circles, because then you can no longer tell what's a cause and what's an effect. And it's really important at this point to get a domain expert to sanity check this graph to determine whether they actually encode causal connections and correct them if that's not the case. And this is an important point, and I'll come back to it. So once we have this graph in step 2, we overlay a probabilistic description of our data according to this graph. So what we get here is a set of conditional distributions that tell us how the value of each variable depends on all the variables that point to it. So in this example, if we're looking at income for a particular company, it will depend on whether there have been new sales, and it will depend on how engaged current customers are. And then we get to the 3rd step, which is the most interesting one, and it's why we've been doing all the work so far. And this step is about asking what if questions. So for this example, what if we make sales managers more specialized on specific products in the company's portfolio? Would that lead to more sales? Would that lead to more income for the company? And it turns out that for this, the usual language of probability is no longer sufficient. And we need something called do calculus. I won't go into the details, but you know, this was invented by Pearl and his students. So if you go through the book of why, he'll talk extensively about this. So this is the 3-step overview, and then now I'll briefly go through each of these 3 steps to give you more detail. So we'll start from step 1, where we have some data and we try to get a graphical structure out of it. And here I'm focusing on a health data set that considers risk factors for heart attacks, which are also called myocardial infarction in the medical world, or MI. So how do we get the graph structure? One option is to go to a doctor, to go to a cardiologist, and ask them to tell us about all the relationships they know about from the literature or from observing patients. So for example, if there's a study that links smoking to hypertension, we would draw an arrow in our graph. But there are a couple of challenges with this. One is that it doesn't really scale well. So here we have 25 variables. So we have roughly 25 squared potential relationships. It's also possible that not all of the links have been studied, but they could still be there. So if we just rely on previous evidence, we may miss some important relationships. So this is where algorithms come in, and their purpose is not to replace experts because they have really valuable knowledge, but it's rather to make their jobs and our jobs easier by finding some of the structure automatically from data. And I'm not going to go into the algorithms for finding the structure, but some of the links I'll have at the end will talk about what we use in CausalNex. And one important takeaway message here is that running one of these algorithms doesn't guarantee that you get a causal graph. And it's really crucial to involve these subject matter experts to review the output and correct it where it's wrong. And this happens in two ways. One is, before even running the algorithm, we could actually constrain the search space. We could forbid certain edges from appearing in the graph, or require that other edges must be in the graph because the evidence is very strong from previous studies. So one example here is that medical conditions shouldn't influence gender. Potentially it could be the other way around, but we know we want to forbid these arrows from appearing in our graph. And then we run the algorithm after putting in these constraints. And then again, we inspect the output, and we might see that some edges should be there, but maybe they should be flipped. And again, there's this iterative process of curating the graph so that it makes causal sense. And this may seem really strange to you if you're used to machine learning as being the kind of thing where the computer does all the work. But it's an essential step because it's what allows us to use observational data. So where we don't have the kind of controlled environment to infer causality. So we can use that observational data, but we still get something that we can interpret in a causal way. And at the end of the process, ideally we would get a graph like this, which captures how different variables depend on each other, and which has been verified by domain experts to allow us to interpret these causally. So this covers step one. And we now have a directed graph that we can work with. And the next step is to learn in a probabilistic way how each node in the graph depends on its parents. And at this step, we have a combination of continuous data like age, categorical data like region that the patient's from, and binary data, so whether somebody has a stent or not. And mixed data types are tricky to handle in general. And we found that discretizing or bucketing all the data is the most flexible and practical way to go here. So we would take our continuous variables and just bucket them. And this is helpful because we don't need to make assumptions about the shape of our continuous distribution, so whether they're Gaussian or gamma or something else. And that is an important step, discretizing the data. So now we're at a point where if you look at each node in the graph individually, we have a histogram associated with it. But we want to look at the conditional probability distribution. So we want to determine the probability of somebody having a stent given their age is A and they are from region R. And we have to do this for all possible ages A and for all possible regions R. And additionally, we would get two probabilities in each case, one for having a stent and one for not having a stent. So in this toy example, when we look at this node, we would get 2 times 2 times 2 probabilities. And the main point here is that fitting these conditional probability distributions, once we've discretized everything, is just an enumeration problem of considering all possibilities. So conceptually, it's straightforward, but the tricky part is doing this efficiently, because if you have a lot of buckets, then you're going to have a lot of numbers to keep track of. But let's get to the most interesting part, which is how we leverage Bayesian networks to answer questions that are relevant for our application. So let's consider this simple graph where I put some possible interpretations for A, B, C, and D, but actually an interesting exercise is to sort of think of other stories you can create that have this graphical structure, and then ask questions about it. So let's go through a couple of different scenarios. In scenario 1, we observe D. So we observed that somebody was admitted to the hospital. And this actually gives us information about everything that happened upstream. So if they were in the hospital, it's probably because they are ill or they have some symptoms. So really observing D changes the distributions of A, B, and C. But this is very different from intervening on D, like in scenario 2. If we take a person from just randomly from the street and put them in the hospital, that won't change the probability of having heart disease. If they were already healthy, they will stay healthy. So this is a really important point, that observing a variable is very different from intervening on one, from forcing it to take a particular value. And okay, in this case, we want to intervene to reduce the risk of stroke. So we might do something like in scenario 3 by intervening on B, by managing somebody's heart disease. So for example, by giving them adequate treatment. And again, you can see that intervening on B will affect the distribution of C. And in CausalNex, it's possible to simultaneously intervene on some nodes and observe others, like in scenario 5. So for instance, we could assess the impact of a specific treatment just on a subset of patients. So just on patients with a high body mass index. And I mean, it's definitely a subjective opinion, but I think this is where CausalNex is really powerful, because you can have these quite sophisticated scenarios, and as long as your graphical structure is reliable, you'll get solid insights out of it. So this is step 3 of our end-to-end causal analysis using Bayesian networks. And I just wanted to touch briefly on time series data, which is basically what I worked on at the start of when I first joined QuantumBlack. And I won't go into a lot of details because it's late evening. There's a Medium post which I put here at the bottom where you can read about this. It's just a 5-minute read. But this paper is about the first step of our 3-step process. So it's about the structural learning part. And it's looking at situations where you don't just have variables that depend on each other in kind of a simultaneous way, but you can have variables now influencing future values, a bit like in the diagram there. And the cool thing with the implementation is that once you've done the structural learning step from time series data, the other 2 steps work exactly the same as before. So the other 2 steps being probability learning and what-if analysis. And this is because ultimately you still get a directed acyclic graph. So you can do everything else in exactly the same way. And this was a whirlwind tour of causal inference using Bayesian networks, and also how I've been learning about these topics over the last couple of years. And I'll leave you with some links where you can learn more. Various colleagues from QuantumBlack wrote these Medium articles where you can learn about CausalNex in general, and also about applications. So in particular, I recommend this one, which which kind of starts from a business problem in a pharmaceutical context, and then explains how causal analysis is relevant. Yeah, also, if you like playing around with Python code, you can give CausalNex a try. There's a tutorial available online, which is quite easy to follow. But honestly, if you don't read any of these Medium articles and you don't use CausalNex, that's okay too. I really hope I convinced you that causal inference is really important in data-driven fields, and that it's a really interesting topic. It's quite vast and kind of can be a bit tricky to grasp. But I also think it's quite exciting, you know, to go beyond the more standard machine learning techniques. So let me wrap up there. I'd be happy to take any questions.
Thank you so much, Roxana. It was really, really interesting, especially for people who are interested in causal inference like I am. You've got the applause there. I will let now people unmute and ask questions.
Maybe while people think about if they have anything to ask, I can explain the acronyms, because I think
especially the dinotears. Yeah.
I'm always amused at like machine learning conferences that people love using complicated acronyms, and then when we were working on our paper, we wanted in with this thing. So so basically our paper is a dynamic version of this no-tiers algorithm, which some people published at NeurIPS 2018. And in their case, I wrote this down because I don't remember it, but in their case, no-tiers stands for non-combinatorial optimization via trace exponential and augmented Lagrangian for structural learning, which is quite a mouthful. But then I found out that they probably use this because there's this other article called Bayesian Networks without tiers. It was published in the early 90s when Bayesian Networks first started. And it's basically an introduction to Bayesian Networks. So that's kind of this whole no tiers started.
It's really nice. My students also like when they find Python libraries with funny names like Beautiful Soup or Snowball or things like that. So it's always good to come up with something that gets stuck in your brain rather than the complicated mouthful. Are you aware of the work of Hol Varian, who is a chief economist in Google right now, and he's been doing some Bayesian structural time series methods, it's a little bit different than yours, but it's for time series, if you have a time series, I can send you some references. He's been doing work there, and they've announced, I have here a paper, and it's from 2014, and since that time it's announced that there is an ongoing work on panel data, which is a combination of time series and cross-sectional data, but I still haven't seen that work out there, which I would be particularly interested in seeing how you would do causal inference when you have both, cross sections and time series. I'm not sure if you are aware of any work that allows for that using machine learning methods, of course.
Yeah, I would appreciate the pointer to the reference. I don't know the work from Google that you mentioned. But yeah, that is a very valid question. Like, what do you do when you have a mix of data? Definitely in our work with clients, they tend to just have data that they collected historically without necessarily having intervened. So that's the more relevant use case for us. But that could change in the future, because I think more companies are getting into this mindset of experimenting. So doing some kind of A/B testing where then, yeah, you'd have a combination of different data types. But yeah, so long story short, I mean, there's so much literature in this field. I don't know that one in particular. And one thing I find is that it's quite, there's a leap going from, academic research to, in our case, we spend maybe 3 months with a client and we need to be able to do things really quickly with data we haven't seen before. So that's a gap that we're always trying to fill.
You have some questions in the chat from Alessandro, if you would have a look.
Yes. So the first question is, how do you check the causal graph? In other words, if A points to B, how do you check that it's not the other way? Okay, so there are different algorithms for doing that and for doing structured learning. And roughly they're classified as what people call score-based and then constraint-based. And the score-based algorithms, they basically just solve an optimization problem. And this is what this no-tiers algorithm does. And then you sort of find the best acyclic graph that fits your data. And there are some, on synthetic data, like under certain assumptions, you can prove that you get the right direction of the arrow, but usually those assumptions don't always hold in the real world. So it's definitely no guarantee that you'll get the right arrow, which is why kind of actually reviewing the graph is quite important. And then, so that's one category of algorithms. And then there are constraint-based algorithms. And those basically check, if I remember right, you basically check that, for example, this node here is conditionally independent from this one, because if they weren't, you'd have to have an arrow from one to the other. So I think those algorithms deal a little bit better with getting the direction right. Yeah, that's kind of the extent of my knowledge there. And then can you please repeat or write the title of the paper? So if you're referring to the Dino-tiers paper, it's actually linked from the Medium article, but the title is Dino-tiers Structural Learning from Time Series Data. And yeah, like I said, it's based on, it kind of expands the method from this other paper, which is called DAGs with no tiers. Yes, that's
the important unobserved variables. It's one of the main reasons for my academic papers being rejected for publication, that I have probably an important unobserved variable. Exactly.
Yeah, I mean, you really hit the nail on the head with that one. So unobserved confounding is probably the hardest thing you can deal with in causal inference.
Yeah.
And I mean, I'm aware of some papers. I know I think there's a group at MIT that works on this. But yeah, it's just really hard to do in general. Yeah, people are working on it, but there's no silver bullet for sure in that case.
I've been struggling for 20, 30 years with that issue, like using traditional statistical methods, and it remains a problem in machine learning as well. So it's, yeah.
Yeah. Any assumption about Gaussian and non-Gaussian variables? So if you're referring to the structural learning step, there are algorithms. Actually, interestingly, there's a method that assumes the kind of noise distributions at each node are anything but Gaussian. You basically need the asymmetry for that particular method. For node tiers, which is, like I said, an optimization method, you don't need to make, well, the algorithm kind of makes that assumption that the noise is Gaussian. But if you check on synthetic data, it actually works quite well with all sorts of types of noise. Yeah, I guess short answer is some algorithms make assumptions about distributions being Gaussian, but they still work quite well when those assumptions don't hold.
Okay. So
Well, I have
think...
two questions.
Yeah, Farah, go on.
Yes. The first question I would like to know, since when the visual network it's been working?
Right. So Bayesian networks, if I remember right, started in the 80s, and I mentioned Judea Pearl as being kind of the person driving this. But I should say that Bayesian networks originally were not intended to be causal objects. It was basically just a way to reason probabilistically about the world.
Yes.
So having those conditional probabilities. And then it was only later that they started as a tool to basically consider the impact of interventions. And
yes.
Yeah, that started being developed in the 90s, but I think it really caught on in the last few years because people realized that to get to the next level with artificial intelligence, you need computers to reason causally. I think there's been a lot of progress recently in getting really good predictions. I don't know, in computer vision, for example, or language and stuff like that. But I think everyone knows now that to push AI further, you need causality. And yeah, it's a hot topic for sure now.
Yes, that's it. And the CausalNex, it can also help the climate field to predict what will happen and all of that.
Ooh, well, I sort of think of this type of analysis not so much as predicting what will happen, but sort of taking a system, understanding how it works, and understanding how to change it in order to achieve a desired outcome.
Okay.
So yeah, I wouldn't. I mean, yeah, you can probably combine it with a predictive mindset, but that, in my mind, that's not the primary use for it. Now, whether you can use that to determine, like sort of along the lines of what Jessica was saying, to determine what's the best action you can take. Yeah, I'm sure you could apply it there as well. But I haven't necessarily seen it.
Okay, thank you, Roxana.
Okay, so I think unless anyone has any other question or comment, we can stop there. Thank you both. Roxana and Jessica is not here with us, but I'll send her a note, thank you note anyway. It was for this great talk late in the evening here, and I guess other parts of the world. Thank you so much, and yeah, now we can go and have some dinner.
Thank you.
Yes, thank you all. Have a lovely evening.
Yeah.
Bye-bye.
Bye-bye.
Bye.